to supplement the calculation. But here, let me redo this one here. So we are given a system mx dot plus cx dot plus kx equal to f of t. Okay, this is the general descriptions, and then for our solutions, xt will be equal to from minus infinity to infinity f tau, and gt minus tau and d tau. Okay, and let me explicitly describe for g. What is g? G is equal to m omega d exponent Okay, so let me explicitly write it up here. So we have to implement this integral explicitly. Okay, and so that is our formula. And for this example, you can see for this example, the f is a constant. So here, for ft equal to constant in this example here, so that's called a step input. Okay, this is called a step function. And if f0 become 1, then we call it unit step functions. Okay, so once we have this one, we simply plug in here because this one simply is a constant. So basically, xt will become simply is this, and from minus infinity to infinity. And let me get all the constant out of the integral m omega d and f0. Okay, and then with the integral is remaining the term here minus theta omega n t minus tau and psi omega d t minus tau d tau.
This might be backing up just here, but why are we doing the integral from infinity to infinity?
Yep, and because here for our time, and we assume we concerned is the covering all the time history for the response. Okay, so basically here that is a tau. Tau basically is the parameter traveling in the time course, and that corresponding is to we concerned all the history of the systems from infinite. Basically, we want to cover all the possible time moments. So that's the reason here. Okay. So we do this one, and so for this simple, very simple time constant, the impulse, the constant step input, then we have to do the integral like this. Okay, even for such a simple shape of the input, that is the one we have to face. And so that's the handouts today I provide to you, and that's my handwritten things. And so we start from here. So this is the one basically we've written here, okay? And so to this, from this moment onward, for this example, it's not my duty of the delivering the vibrations. However, that is basically depends on our capability of implementing the integral, and which should be covered in Calc 1, Calc 2, or even Calc 3, right? Okay, so here I put something. So do partial integral twice, okay, twice. And then even for this one, that took me about 20 more minutes by handwriting. And that is a story where originally I used oil pen to write something, and I keep constantly making mistakes and writing something wrong. I changed the pencil. But again, I erase. I with the erasers get ready. I get so frustrated. On one side, a lot of writing. On the other side, when do this the calculation, I constantly make mistake, and I know the mistake. I erase it. So eventually, I do the calculation in Word documents. I simply copy and paste from the previous step to the next one, and I minorly change something, and then I proceed. I found this way is much quicker. It saves me a lot of time, and that is the one I give you the handouts, the homework 11, so something like this one. Okay. So this is the answer. Okay, and the handouts I provide to you, basically that is the detailed calculation, and that the method in handouts today, and that is not unique. This is not the unique calculation process. I believe everyone you have your own kind of preference in doing something. So this is only for your reference, but I believe this should be correct. Okay. So this is the result like this, okay? And for this result, and we pay attention a little bit more about these solutions, okay? First of all, you can see this is our xt. Okay, so that is our solutions, and let me box it. And I want to make an important count the points here. Here we are given a system like this, and assuming the f is a constant like this, then we have such a result. Okay, so if you pay attention to here, so let me rewrite this province. Basically, the province becomes like this, f now. Right? F now is constant. Have you been familiar with this type of problem before? Yes, right? Somewhere in previous chapters. And do you remember what we've been dealing with over there? Let me write it up and to try to bring up your memories, okay? We know this one, we have the x of t equal to capital X, and then cosine. Let me make a dummy one. Okay, so say f cosine omega b. So we have this one. This is basically this is cosine and omega t minus v. And if you remember, and we have such a formula, capital X equal to k and 1 minus r squared plus 2 zeta r squared, and v equal to arctangents, and 2 zeta r and minus r squared, and r equal to omega divided by omega. We have a such formula, right? Okay, and for the constant, for our example here, you simply replace omega equal to 0 in all the calculations, right? And hopefully you still have some kind of the memories about this one. Doesn't have to be exactly, but right, we have such done this one. So we can try a little bit to see what will be the result compared to this one. And that is the comment I want to make. Okay. So for this case, we plug in omega equal to 0. So basically here, these calculations will be when omega equal to 0, then this calculation will be equal to 0, and this one will be equal to f now divided by k, right? And this one should be equal to 0. So basically, our result is this. Xt will be equal to fk now divided by k times, and that's it. This is the result. Okay, if from chapter 3, we applied what we learned from chapter 3, we got the result like this. In these chapters, if we apply very rigorous integral, something like this one, we got the result like this. What's the difference between the two results? And which one you trust? Why the same problems, they give us the two different results? And do I make a mistake again today? Or have been making the big mistake through almost all the semesters in front of you? I think that'll be a whole disaster. Can you see why they give us such different things? I think this one worth a lot of the bonus points.
Is it?
Yes.
So does the F naught on the slide start at 0?
Yes. No. It's right away when t equal to 0, it's just right away starting
Yeah, exactly.
from. Yeah. And so I would say this is t plus, and when t minus is from 0.
But that's different than here.
This is again. This is the f now. This is constant.
Across all.
Yes.
Yeah,
So that could be one reason. That could be one reason. Yes, that is the one reason. One of the reasons. And
In this case, omega is 0.
yes, and the same
okay.
is omega is 0. Yes. I think this one is the moment I want to. A good moment for me to reinforce a very fundamental concept. And the one before I do that one, let me do a little bit more observation from this result. Okay. For this result, if we calculate initial when time equal to 0, if you plug in here, that basically is f equal to k and 1 minus, and when we introduce in time equal to 0, basically that is equal to 1 equal to 0. Okay, so that's it. When we calculate the initial velocity, and again, if you spend a little bit 1 or 2 more minutes, and by placing the t equal to 0, you will find initial velocity also equal to 0. Okay, so basically, this is the solutions of these problems. Satisfied with this is the solution satisfy these conditions. So I would say, for clarify, I would say this one is the total solutions. And total solution, that means including the transient response and the steady state, I would say the transient response and the particular solutions, and that satisfy both the non-homogeneous term as well as particular initial conditions. This one, we can put these things here. This is called the particular solutions. Particular solution, you know from learning the differential equations, particular solution is only part of the whole solutions, right? So basically here I want to emphasize is the difference between the two forms here. In chapter 3, what we have done, what we have learned in chapter 3 is to associate, we focus on the particular solutions. We don't care whether that solution will satisfy initial condition or not. We only care about particular solutions. So in that regard, and all the techniques in chapter 3 applies. Okay. For this one, basically I think the result, let me put a label here. So that should be where the label is total. Like this. Okay, so that's the difference. So basically this information result being obtained by implementing the convolutional integral provide us more information, I would say the correct and exactly correct information, that including everything here. So I would say this one is a very powerful method. It automatically covers everything. Okay? And this is for, in particular, is for spatial initial conditions. And if you remember, for this kind of things, particularly the initial condition are zeros, basically this one, okay, let me draw that, so I will mention this to you later. We good? Okay. Any other questions? No? Okay, then I want to present to you another approach to the same questions here. Okay? And so how we can have the new sections.